So, thank you, Mr. Chairman. So this presentation treats about an experimental study on RC columns retrofitted by FRP, and for some of them with Henencourt CFRP strengthening system and subjected to seismic loading. So first of all, I present the context and the objectives of the study, then the experimental program and results, and finally I'll talk about a proposal to amend some design rules and conclusions and perspectives. So it was put forward many years ago that we need specific seismic detailing requirements if any earthquake occurs, and especially for columns, which are a major cause of construction collapse. So for new construction, new rules with high ratio of internal reinforcement have been developed, but for all construction where the internal ratio can be changed, new rules have to be introduced. And as an example, the creation of an external reinforcement by FRP. So concerning the external reinforcement, we can find many studies about confinement efficiency, but for seismic strengthening, we need both confinement and flexural strengthening. So the objectives of the study are to analyze the behavior of RC columns depending on the FRP confinement and depending on the flexural reinforcement. And so the aim is to determine the influence of these parameters on the ultimate strength, the ductility, the stiffness, and the dissipated energy. So for this program, 8 wheel scale RC columns were realized in the laboratory of Fifth Star Paris. So the column have a height of 2.5 meters, and there was a huge RC stub. So we applied different strengthening configurations. So the first one is without strengthening, then one layer of CFRP sheets, then one layer of CFRP sheets in addition with CFRP plates, and finally one layer of CFRP sheets in addition with anchored CFRP plates. Note that for each configuration we realized and tested 2 specimens for a better reliability. So just some precisions about the last strengthening configuration. So an innovative encrypt system was developed in cooperation with Freycinet company. So from a usual CFRP plate, the hand of the plate was modified, and the carbon fibers are reassembled into a cylinder shape, and so this hand of the plate can be anchored in the stub. Note that before being applied on the RC columns, this innovative system was firstly tested on small concrete blocks with shear test. So here on this slide you can see the application of CFRP sheets and CFRP plates. Concerning the loading procedure, the seismic load is simulated by a constant axial load of 700 kN, which is approximately 20% of the axial load carrying capacity, and by cyclic lateral displacement gradually increasing. So here you can see on this slide, on red, the system who applies the axial load with a pair of hydraulic jack linked to pre-stressed tendons, and in green a bigger hydraulic jack which applies the lateral load. So huge instrumentation was displayed on the specimen. So concrete, FRP, street strains at different locations, deflection along the specimen, and axial and lateral load were recorded during tests. So concerning the experimental results, so for non-retrofitted specimens, we observed a huge spalling of cover concrete, a buckling of longitudinal reinforcements, and a loss of vertical load carrying capacity for a drift ratio of 6%. For retrofitted specimens, we also observed a huge cracking at the junction and the formation of a plastic hinge, the buckling of, and then the rupture of longitudinal bars, and specimens were tested until a ratio of 10%. More especially concerning RC columns with the anchored plates, we observed a premature failure of anchorage with the crushing of unanchored parts when the anchored plates were loaded in compression. So here you can see, non, ça marche pas. A video of the test in progress. So if we have a look on the envelope curves, we can see that the ultimate lateral displacement for strengthened columns is about twice the ultimate lateral displacement of non-retrofitted specimens. So it shows that the strengthening configuration can enhance the ductility of the columns. We can also see that there's a similar post-peak behavior. So we can, it seems that in our case the confinement is the main strengthening system which can enhance the ductility. We can see that there's a strength enhancement for anchored plates of about 40% compared to the maximum lateral load of non-retrofitted specimens. But as shown previously, we observed a premature failure of the anchored plates when loaded in compression. So from this point, the anchored plates are totally inefficient. So that's why we, after this strength enhancement, we find the same similar post behavior. Concerning the stiffness, we can see that the initial stiffness is lower for non-retrofitted specimen, but there's a small difference between different retrofitted specimens. We can also observe that there's a degradation of the ratio actual stiffness on initial stiffness. And finally, we observed that there was no difference between the strengthening configurations in terms of energy absorption capacity. So finally, as a conclusion to these experimental results, we can say that thanks to reinforcement, we can have a huge increase in ductility and energetic performances, whatever the configuration of reinforcement. However, in our case, we have seen that unanchored CFRP plates are ineffective, but in the same time, anchored CFRP plates can be an interesting solution, and they could improve the load capacity, but the system needs to be improved to prevent from premature failure in compression. So now, if we have a look on design rules, we've seen that for ductile elements and especially for columns, capacities shall be based on ultimate deformations, which are defined in terms of the chord rotation. So in that way, works of Bitskinis and Fardis served as the basis of Eurocode 8. And so we wanted to apply these works on our specimens to check if theoretical results could correctly predict experimental results. So we've calculated the theoretical chord rotation and drift for the different specimens. So here you can see the formulae of Bitskinis and Fardis works. For non-retrofitted specimens, and the same formulae are used in Eurocode 8 with the introduction of the safety factor gamma L. So if we plot this theoretical value on our envelope curves, we can see that the theoretical deflection at yield and the theoretical ultimate deflection are quite the same as the experimental ones if we use the formulae from Biskinis and Fardis. And if we had the safety factor from Eurocode 8, we can see that the theoretical deflection at yield is still the same as the experimental one, but the theoretical ultimate deflection is lower than the experimental one and is about 77% and 60% of the maximum lateral load. Now for retrofitted specimens, you can see here the formulae from Biskinis and Fardis, and with the introduction of a TC, the term relating to confinement, and once again the same formulae are used in Eurocode 8 with the introduction of gamma L. So here again, if we plot these theoretical values on the envelope curves, we can see on the right that with Biskinis and Fardis works, we have an understatement of ultimate deflections, which is underscored by safety factors of Eurocode 8. So finally, we can say that the approach of Eurocode 8 is conservative, but it seems that it's possible to adjust this theoretical value of the code rotation according to the load dump which is expected to have the same level of safety between retrofitted and unretrofitted specimens. So we've proposed a modification of the parameter CF in the term relating to the confinement, which is expressed from our experimental results. So finally, we've seen that FRP could be a good solution for the reinforcement of columns, but it's also very important to reinforce the column stop junction. So that's why we've developed this innovative anchoring system for CFRP plates. From that, we realized an experimental campaign on 8 representative scalar C columns, unretrofitted and retrofitted with different strengthening configurations. It appeared that we could have an improvement of ductility for retrofitted specimens. We also observed that the damage zone was concentrated at the junction footing column with the formation of the plastic hinge. We also observed that in our case, unanchored CFRP plates were inefficient, and that anchored plates can provide an increase of lateral load carrying capacity, even if the benefits are limited due to the premature failure of the anchorage by crushing. And finally, we observed a good approximation of experimental results with capacity design. So the perspectives of this work could be to propose some improvement for the anchoring system of FRP laminates, and to make some additional tests with an optimized strengthening configuration, like a decreasing confinement, for example. Thank you for your attention.